Hello and welcome. In this problem, we have a rigid tank containing some moist air, and the condition of the moist air is given. The volume of the tank, the temperature and pressure. In addition, it's said that the air is saturated, that is, relative humidity is 100%. Now we are heating this tank to a pretty high temperature of 100 degrees Celsius. We are supposed to find the final relative humidity. We are supposed to find the final pressure and the heat transfer during the process. Obviously, a psychrometric chart cannot be used for this problem because the total pressure in a psychrometric chart doesn't change. I've already solved the problem, so I'll just take you through the process. It's really simple. First of all, the correct app for this is you go to the TESTapp page, and there you follow it's a closed process. So follow the closed branch, but the closed process for psychrometric is handled in a specific branch because it has it's specialized. It involves specialized knowledge, and clicking there brings up the hands-on example page, and going there takes you to the app. So for state 1, the total pressure is supplied. If you recall, the volume of the tank is supplied, which is mass volume is supplied right here, and the temperature is given, as well as the relative humidity is 100%. Yes, there are too many properties for psychrometric for moist air, but once you get the hang of it, you realize that, for instance, the pressure is broken up into the pressure of dry air, vapor pressure, and saturation pressure. Temperature has dry bulb temperature. This is the dry bulb temperature. There is dew point temperature, wet bulb temperature. So there's a pattern in this. So for state 1, it's completely calculated, but and for state 2, we know we can solve it many different ways. We don't know the pressure. However, we know the rigid tank, so the volume not going to change. It's same as volume 1. Next, what we know, the final temperature is given to us. We don't know the relative humidity. If you know what omega is, you could write omega 2 equals omega 1 because the ratio of the amount of vapor and dry air. Or you can directly write, what in this tank, the mass of dry air doesn't change. We're just heating, and mass of vapor doesn't change. So this is another way of expressing the same thing. And you will find that as a result, the final pressure is found and final relative humidity is found, which is only less than 4%. And finally, to get the heat transfer, by the way, you can go to the graphics panel, and of course, this will not be correct because this particular line is for total pressure of 100 kPa. In the process panel, we are setting up the process. Again, this is meant for a complicated system. In this case, it can handle 2 different subsystems, but we have a single subsystem, so we just the beginning state is state 1, final state is state 2. We left the other one state null. That is, we have moist air here going to moist air. It is designed in the fashion that if you had 2 different tanks of moist air connected, then you could have 2 subsystems. Anyway, we don't have subsystems in this problem. State 1 to state 2, and there is no external work transfer. A calculate produces heat transfer in kilojoules. You can convert the unit to any other unit you want. So solving this problem is nothing different from any other closed process problem, except it involves moist air and therefore a number of complicated concepts. But imagine this same problem, instead of heating, we're cooling. Then the problem will become a lot more complicated, because in that case, what will happen, there may be a possibility of condensation. In that case, the final state will have moist air and some H2O, liquid H2O. So that's how the app is designed in this manner. In the next problem, we'll solve a similar problem where we'll have condensation in a closed system.